0. In this video presentation, I will be talking about Chapter 12, which is about metal casting, design, material, and its economics. In this section, we highlight why casting remains one of the most essential manufacturing processes. Casting allows us to produce shapes that cannot be achieved by other methods, especially components that are large, complex, or require internal cavities. We also emphasize that casting works with many metals like aluminum, steel, magnesium, copper alloys, and more. Because each casting process has unique characteristics, selecting the right method depends on factors such as part size, metal being used, require accuracy, and production volume. This set a foundation for understanding how design, materials, and economics influence casting quality and cost. This section focuses on how the geometry of the casting affects its final quality. Poor design choices often lead to defects like shrinkage cavities, porosity on hot spots. To avoid this, designer must control section thickness, provide smooth transition, and plan solidification so that metal freezes directionally toward the risers. Understanding how molten metal behaves inside the mold, how it flows, cools, and solidifies, is critical to producing sound casting with minimal scrap. The fundamental rule of casting designs are presented here. Uniform section thickness helps promote even solidification and minimize defects. Sharp corners should be avoided because they concentrate stress and create local overheating, which may lead to cracking or shrinkage problems. Gradual transition between thick and thin areas improve metal flows and solidification quality. Overall, these rules help ensure structural integrity and reduce internal defects. In this continuation, we focus on manufacturability. Reducing complexity helps produce more reliable molds and improve metal flows. Draft angles are essential. Without them, patterns cannot be removed from the mold without damage, especially in sand casting. Proper placement of gates, risers, and vents must also be considered early in the design stage because they control the flow and feeding of molten metal. These features ensure good quality and help avoid rework or rejected casting. Figure 12.1 from the page 296 is the suggested design modifications to avoid defects in casting. Here, on the left of each one is the prompt quality, versus the one on the right is the good quality. Moving on, here are the illustrations of examples of designs showing the importance of maintaining uniform floors. Sections in casting to avoid hot spots and shrinkage cavity. Now we have table 12.1 from page 297, which is the normal shrinkage allowance for some metal cast and samples. So for example, the first one is a gray cast iron, and the shrinkage allowance is between 0.83 till 1.3%. And the highest one being high manganese steel, which the shrinkage allowance is 2.6%. Expandable molds, like sand, shells, or investment molds, are destroyed after each use. Because of this, designer must include several types of allowances in their pattern. Shrinkage allowance for cooling contraction, machining allowance, draft allowance, and distortion allowance. Pores are often used to create internal cavities and complex geometries. Mold permeability and venting are also crucial because gases must escape without causing porosity. This slide outlines the additional allowances required specifically for expandable molds. Machining allowance ensures that surface can be finished without removing too much material. Draft allowance assemble pattern removal, while distortion allowance compensates for warping caused by uneven cooling. Venting is vital to prevent gas defects, and proper mold permeability helps gases escape during pouring. Permanent molds are reusable and made from metal, meaning they must withstand repeating thermal cycling. This repetitive heating and cooling can cause thermal fatigue, so designs must avoid sharp corners that concentrate heat. The higher cooling rate in permanent molds produce finer grain structure and better mechanical properties. Designer must also plan for ejector pins, which aid in removing the part from the mold. Permanent mold gives superior surface finish and dimensional accuracy compared to sand molds. However, their geometry is more restricted because the mold cannot deform to release complex shapes. sharp corners increases mold wear, reducing tool life. Therefore, part design must consider mold longevity, manufacturability, and ease of injection. Computer simulation has become a critical tool in modern casting engineering. It predicts metal flow, temperature gradients, solidification time, and the formation of defects like shrinkage, porosity, and turbulence-related issues. Simulation provides insights that are impossible to see inside a real mold, helping engineers optimize gate and risers designed for manufacturing tooling. By using modeling software, engineers reduce trial and error, saving both time and cost. Virtual prototypes can be tested under different pouring conditions, mold materials, and geometries. This minimizes scrap rates, improves casting quality, and speeds up production development. Simulation is now a standard step in competitive casting industries. This section introduces the key alloy properties required for successful casting. Good castability depends on the alloy's fluidity, solidification behavior, shrinkage characteristics, machinability, and tendency to crack. Alloy selection also considers costs and the operating environment of the final product. Understanding these factors allows engineers to choose the most economical and reliable alloy for casting. Non-ferrous alloys are widely used due to their excellent casting properties. Aluminum alloys are lightweight and corrosion resistant, making them ideal for automotive and aerospace components. Magnesium alloys are even lighter, though less commonly used due to their reactivity. Copper-based alloys provide strong wear resistance and excellent thermal and electrical conductivity. Zinc alloys are extremely fluid and perfect for high-precision die casting. Titanium alloys offer outstanding strength and corrosion resistance, but require strict process control because of their high reactivity at molten temperature. Each non-ferrous alloy type provides unique benefits that match specific product requirements. Now in this slide, we have a graph. A is the UTS, or ultimate tensile strength. For many types of metals, there are steel, metallar iron, gray iron, and so on and so forth. We also have the yield strength in V for each one of the metal that I said before. And we have the modulus of elasticity of each one of them, with nickel base and cast steel being one of the highest one, and magnesium base being one of the lowest. Next in D, we have them in comparison to the wars and cast. In this slide, there is the impact energy for F. For E, there is the final hardness, elongation, and also reduction of area or shrinkage. Table 12.2, typical applications for casting and casting characteristic. This table summarizes how different metal alloys behave during the casting process and where they are commonly applied. It gives us a quick comparison of three important characteristics: castability, weldability, and machinability, along with typical end-use application. First, notice that each alloy type is listed with real-world examples, such as pistons, pump housing, transmission housing, turbines, brake shoes, and valve components. This helps us understand why certain alloys dominate specific industries. Castability tells us how easily the molten metal fills the mold without defects. Aluminum and zinc shows excellent castability, which is why they appear often in automotive and consumer product casting. Gray cast iron also has very good castability, making it widely used for engine blocks, machine bays, and brake rotors. Weldability indicates how well the alloy can be welded after casting. Some materials like steel have very good weldability, while others, especially cast iron, are more difficult to weld due to their carbon content and risk of cracking. Machinability shows how easily the final part can be machined to achieve tight tolerance. Aluminium, magnesium, and zinc alloys machine very easily. White iron, however, has very poor machinability because of its hard, brittle microstructure. The key takeaway is that no single alloy excels in all categories. Designers must balance castability, weldability, and machinability depending on the function and manufacturing requirements of the part. This table helps engineers select the most appropriate alloy based not only on mechanical performance, but also on how efficiently it can be produced and finished. It reinforces the idea that material choice has a direct impact on casting quality, ease of fabrication, and overall manufacturing cost. Now, Table 12.3 is the properties and typical applications of cast iron. And here we have the UTS, ultimate tensile strength, we have the yield strength, elongation in 50 millimeters, and also the use for the real world or the typical applications. This table presents the mechanical properties of different classes of gray cast iron, categorized according to the ASTM standards. Gray cast iron is widely used because of its excellent castability, vibration damping, and good machinability, but its properties vary significantly depending on its class. First, look at the trend across ASTM class numbers, from 20 up to 60. As the class number increases, the strength and hardness also increases. This means higher class gray cast iron are stronger, harder, and more resistant to deformation. Key observations. First, we are going to be talking about the UTS, ultimate tensile strength, increases from 152 MPa, class 20, to 431 MPa, class 60. Gray cast iron is generally weak in tension due to its graphite-like structure, but higher grade provides better performance where tensile loads are present. Comparison strength significantly higher than tensile strength for all classes, ranges from 572 MPa up to 1,293 MPa. This reflects why gray cast iron is preferred for components under compressive loads such as machine bases, engine blocks, and brake components. Elastic modulus increases moderately from 66 to 97 GPa in class 20 to 141 to 162 GPa in class 60. A higher elastic modulus indicates greater stiffness. This property is important for structural improved stability and dimensional rigidity. Hardness HB rises steadily from 156 HB to 302 HB with increasing grade. Powder iron provide better wear resistance but are more difficult to machine. This helps engineers choose the right balance between durability and machinability. Higher ASTM classes of gray cast iron provides better mechanical performance, greater strength, stiffness, and hardness, but may sacrifice machinability. Engineers select a specific class depending on the requirement combination of load-bearing capability, wear resistance, and manufacturability for the intended application. This table helps us understand why different grades are chosen for different industrial components, depending on the mechanical demands placed on the part. Now, Table 12.5 is the properties and typical application of non-ferrous cast iron. The alloys in UNS, there is the condition, the UTS, yield strength, elongation, and the type of application that is used or that will be used. Ferrous alloys include cast iron, carbon steels, alloy steels, and stainless steels. Cast irons are the easiest to cast due to their fluidity and lower melting temperature. Carbon and alloy steels provide superior strength but are more difficult to cast because they shrink more and require higher pouring temperatures. Stainless steels resist corrosion well but demand precise temperature control during casting. Casting economics involves balancing tooling costs, material costs, process efficiency, and finishing needs. Pattern making, mold production, melting, curing, and post-processing all contribute to total cost. High scrap or rework rates significantly increases expenses. Therefore, good design directly translates to lower production costs and higher reliability. High-volume production benefits from permanent molds, die casting, and automation because the tooling cost is spread over many parts. Low-volume production favors sand or investment casting, which require lower upfront investment. Process selection must therefore match production quantity and require quality to be economically viable. Table 12.6 General table compares different casting process based on three main cost categories: die cost, equipment cost, and labor cost, as well as their typical production rate. This comparison helps engineers choose the most economical process for a given production volume. First, sand casting. The cost is low die cost, low equipment cost, and low to medium labor cost. The production rate is very low, typically under 20 pieces an hour, meaning best for large, simple parts or low volume production where tooling costs must be minimized. Moving on, shell mold casting. Cost is slightly higher die and equipment compared to sand. Production rate is low. It is below 50 pieces an hour, meaning offers better surface finish and accuracy than sand casting, but with a higher cost. Then we have plaster casting, the low to medium die cost, medium equipment cost, and medium to high labor cost. Production rate is still the same, which is very low, below 10 pieces an hour, meaning it is ideal for precision shapes in low quantities. It is not suitable for mass production. Investment casting. Cost is medium to high die cost, medium to high equipment cost, and high labor cost. Production rate is moderate, somewhere below 1,000 pieces an hour. It is excellent for complex, high precision parts. It is economically mainly for small components or high value materials. Permanent mold casting. Cost is medium die cost, medium equipment cost, and low to medium labor cost. Production rate is still low, somewhere between under 60 pieces an hour, meaning it's higher initial investment, but good accuracy and surface finish makes it suitable for medium volume production. Moving on to die casting, it is a high die cost, high equipment cost, but low to medium labor cost. Production rate for it is usually very high, up to under 200 pieces an hour. It is very economical for mass production, especially for non-ferrous alloys like aluminum, magnesium, and zinc. Lastly, we have centrifugal casting. The cost is medium die cost, high equipment cost, and low to medium labor cost. Production rate is still under 50 pieces an hour. It is ideal for cylindrical components which require high density and good mechanical properties. The key takeaway for this table is no single casting process is best universally. Low die cost is best for low volume production, such as sand and plaster. High die and equipment cost is justified only for high production rate, such as die casting, and labor cost varies based on complexity and automation level. Understanding these cost relationships helps engineers select a casting method that balances quality, speed, and total manufacturing cost. Finally, we move on to summary. This slide highlights the key points covered throughout the chapters. First, remember that casting is an extremely versatile manufacturing process. It allows us to produce complex shapes, including hollow and intricate components, using a wide range of alloys, from aluminum and magnesium to cast iron and steels. Good design plays a crucial role in casting quality. By controlling section thickness, avoiding sharp corners, and planning proper metal flows and solidification, we can significantly reduce defects such as porosity, shrinkage cavities, and hot spots. Sound design directly improves castability and reliability. Each casting process has its own design rules and limitations. For example, sand casting allows for very complex shape but require large draft angles, while permanent mold and die casting processes demand simpler geometries due to mold rigidity. Understanding these differences helps engineers choose the right process for the right job. Computer simulation has become a powerful tool for modern casting. It allows us to visualize metal flow, predict solidification patterns, and identify potential defects early, reducing trial and error and lowering production costs. Alloy selection is also critical. Different metals offer different fluidity, shrinkage behavior, machinability, and final mechanical properties. Choosing the right alloy ensures consistent performance and minimizes processing challenges. Finally, economic success comes from aligning the design, the alloy, and the casting process with the production requirements. When all three are matched correctly, casting becomes an efficient, cost-effective method for producing high-quality components. Thank you for your attention. This concludes the Chapter 12 presentation on metal casting design, materials, and economics.